Hello everyone, today we continue our discussion on optimization. We try to solve this problem. A cylinder is inscribed in a right circular cone of height 2.5 centimeters and radius at the base 2.5 centimeters. What are the dimensions of such a cylinder which has maximum volume? To solve this problem, we might first want to draw a diagram. Now here is our right circular cone in green, and here is our cylinder inscribed in it in red. We can let the height of the cylinder be given by the letter H, and the radius of the cylinder be given by the letter R. The height of the cone is 2.5 cylinder, and the radius of the base half of the cone is 2.5 centimeters. Now, if we were to take the cylinder and take a sideways view of it, it will look something like this triangle. And if we should input this or place this on an XY coordinate plane, we could set up some measurements in it. So for the radius, if we fix it on the y-axis, centered at the y-axis, the radius could be measured along the x-axis. Maximum radius there of 2.5, and the height on the y-axis up to 2.5. So this is what the side view would look like on the coordinate plane. We place our R on the x-axis and H on the y-axis. Now recall the volume of the cylinder, V is equal to pi R squared H. We want to express H in terms of R because we only want to have one variable on the right side when we need to do our derivatives. So if we look at the diagram that we had placed on our coordinate axis, the y coordinate will represent our h values, the x coordinate will represent our r values. Y is equal to mx plus b. Y is equal to mx plus b. And looking at the slant line, which will represent the slant height of our cone, right there, or m would be equal to -1, b would be equal to 2.5, so y would be equal to -x plus 2.5. Expressing that in terms of h and r, we can say h is equal to -r plus 2.5. Now we can plug this into the volume equation. V of r will then be equal to pi r squared times -r plus 2.5, and then we can expand that a little bit. V of r will be equal to negative pi r cubed plus 2.5 pi r squared. Now we want to find our maximum r. In that case, I'm going to take the derivative and set the derivative equal to 0, and then try to solve for r. The derivative v prime of r will be equal to negative 3 pi r squared plus 5 pi r. Then, setting that equal to 0, what we'll have is negative 3 pi r squared plus 5 pi r equal to 0, and the rest is just a bit of algebra. Solving for that, pi r is equal to 0, then r is equal to 0. Negative 3 r plus 5 equals 0, then r will be equal to 5 over 3. Now we need to choose which of these is the maximum. Is it r is equal to 0 or r is equal to 5 over 3? We could use the first derivative test here, and that will show that your r equals 5 over 3 is the maximum. Or intuitively, we want to say, r equals 0 does not really make a lot of sense in this situation. But either way, think about it, we know that eventually your r is equal to 5 over 3. That is the best answer. Now what about h? H should be equal to 2.5 minus 5 over 3, and that would be equal to 5 over 6 centimeters, and we're done. Let us look at another problem. Find two positive numbers that satisfy the given requirements. The product is 48, and the sum of the first plus 3 times the second is a minimum. Let the numbers be x and y. For the product, x times y equals 48. For the sum, s equals x plus 3y. We want to minimize this sum, so we solve the product for y and plug that into the sum function. From the product function, y will be equal to 48 over x. Plug this value of y into the sum function, so we have s is equal to x plus 3 times 48 over x, and we can try to simplify that a little bit. So the s is equal to x plus 144 over x. Now, in order to find a maximum or a minimum, we find the derivative of the function, then set it equal to 0. The derivative ds dx is equal to 1 minus 144 x raised to the negative 2, which we can write as 1 minus 144 over x squared. Then we set this 1 minus 144 over x squared equal to 0 and solve for x. So 1 is equal to 144 over x squared. 1 over 144 is equal to 1 over x squared. And so x squared will be equal to 144. X will be equal to plus or minus the square root of 144. Should be equal to plus or minus 12, but because we want a positive root, we choose x equals 12. Then we try to solve for y. Y, we remember, is equal to 48 over x, so that would be equal to 48 over 12, so y is equal to 4. Now, because the second derivative is positive, the sum then would be a minimum when x is equal to 12 and y equals 4, and we're done. Let us try to solve another problem. Find a point on the curve y is equal to radical x that is closest to the point 3, 0. In order to solve this problem, we might first want to sketch a graph of y is equal to radical x. And on that graph, identify the point 3, 0. So here is a graph of y is equal to radical x. Starts at the origin and goes up, curves to the right, curving to the right, going towards infinity. The point 3, 0 is on the x-axis. We want to find the point that is closest to 3, 0, but on the graph of y is equal to x. We can identify an unknown point on the graph of y is equal to radical x. That unidentified point will be x radical x for your x and y values. These are numerical values which we later on want to find for these. Okay, so from our point x radical x, we want to draw a straight line, and let's call that d, and that d will be our minimum distance from x radical x to 3, 0. We can drop a vertical from x radical x down to the x-axis, and so if we connect where that point is on the x-axis horizontally to 3, 0, we're making a right triangle here in green. The point where the vertical from x radical x hits the x-axis The difference between that and the 0.30 will be a difference of 3 minus x units. So then we can pull this right triangle out, and let's try to find some distances. Okay, so from that right triangle, we have the hypotenuse, we label that D. The vertical from x radical x all the way down to the x-axis, that distance will be radical x, and then the base here will be 3 minus x. By Pythagorean theorem, the hypotenuse squared will be equal to the square root of the sum of the legs squared. So D will be equal to square root 3 minus x all squared plus radical x all squared. Our feasible domain on a square root function will be 0 included to infinity. Simplifying this distance formula here for D, we have D is equal to square root of 3 minus x all squared plus x. Continuing our work down, we want to take the derivative and then set that derivative is equal to 0. So the derivative, we call that d prime, is equal to 1/2 parentheses 3 minus x all squared plus x raised to the negative 1/2 times 2 parentheses 3 minus x parentheses times negative 1. Now, we want to rewrite this a little bit so that it'd be nice to set it equal to 0. So let's rewrite a 1/2 times negative 2 times 3 minus x plus 1 all over radical 3 minus x all squared plus x. And then that would be negative 6 plus 2x plus 1 all over 2 times radical 3 minus x all squared plus x. And then keep on simplifying, that's 2x minus 5 over 2 radical 3 minus x all squared plus x, and then setting that equal to 0. And simplifying, we end up with 2x minus 5 equals 0, so x will be equal to 5 over 2. If x is equal to 5 over 2, then y is equal to radical x, so y is equal to radical 5/2. And so the point closest to 3, is 5 over 2 parentheses, comma, radical 5 over 2. And so we have found our answer right here. Thanks for watching. Like, subscribe, and see you next lesson.